Everybody, Mr. Smith here in my kitchen shooting another video lesson for you guys. And in this lesson, we're going to learn a very useful skill, finding the shortest distance to a line. And we'll talk about why this application can be really important. But yeah, as usual, guys, shooting in my kitchen, got the dog around, might be a distraction. The kids are downstairs watching Beethoven the movie, the one about the dog, not the composer. And at any time, we could have a little one coming up here to go to the bathroom or do whatever. So I'll get them to say hi, and then we'll just plow on. Yeah, I actually really enjoy teaching this lesson. So I think it's a really cool idea. Let's get started. If you can imagine, and there's lots of these going up, if you can imagine, say, like some new suburbs going in, like just like a bunch of new houses, right? And let's say you've got, like, here's just the road. My best impression of road. You don't have to draw this. Yeah, there. Let's say that's a road, right? And then along this road, you've got the power lines, right? So usually they're in kind of like a straight line. You can imagine that being a straight line. But let's say you have a new house being built right here. And you can imagine this being like the power lines or even like the main water line or something like that. And you have to connect the house from the main power line, and you have to connect the power to that house. So you got to take some cables and hook it up. So visualize, guys. Would I make the connection? Like, would I go from, like, let's say that the hookup's like right here. Would I make my connection like that? Or is there a route that minimizes the amount of cable I can use? So is that a good idea? Maybe that's a bit better. It uses a bit less cable. Do you guys see the shortest possible route? How could you minimize the amount of like cable you have to use to connect the house? Do you guys see it? It'd be like that. It'd be perpendicular to the power line, right? This would minimize the amount of wiring you have to do. And if you can imagine, if you had a ton of houses, right, that minimizes the amount of power line, and that minimizes the amount of labor that it would take the people to lay that power line, and it would save a lot of money in the long run. So what we want to do today is find a way. So given a line, so let's say your power line was at a line in like y equals mx plus b form, and where you're inserting the power is a point. We want to know exactly where to, like, what is the shortest distance from that point to that line, and kind of figure out, like, where would we hook, like in this case, where would we hook up that power, or like where is the shortest distance? So it's a useful question. That's kind of what we're doing. And our entire lesson today is just one example. And then those of you who are in my class I'll have another walkthrough for you to try on your own. But here's our scenario. So we have a ranger cabin, and it's located, you can see the R is for the ranger cabin. So its coordinates, you can see, are at 6, 1.5. And the ranger cabin is built near a straight road. And that road, you can see, runs from this campground from A, to this campground from B. So that's the road we have. And A is at the point 2, 8.5. B is at the point 10, 4.5. And again, the cabin is 6, 1.5. What we're doing is we're going to connect this cabin site to the campground road with a side road. And obviously, to minimize, as we mentioned, to minimize the construction materials for the road, the labor it would take, how much like forest maybe you have to chop down and get through, you want to find the shortest route. You want to know exactly what point to connect the road to, so that, yeah, it's the shortest route. So based on our discussion from earlier, And this is the key idea. And again, we're going to make use of, we're letting every point or every unit on the map is 500 meters. We'll make use of that later. But our goal is to find the shortest route. And the key idea we talked about earlier, the shortest distance from a point to a line is always perpendicular to that line. So, didn't mean to draw that. So what's the shortest distance here? Let's just rough it out. This isn't solving the problem. This is getting an estimate of what the idea here is. So you can see me tilting my head. I'm just looking, okay, what would be perpendicular to this line? So I'm just carefully drawing. It looks like that is pretty perpendicular. It looks to me like the point 8 and 5.5. That looks about where the shortest distance would be. But of course, in this course, that academic course, we're not about just estimating. Estimating is good to get a good idea. We want to know precisely where to connect this road. And that's what we're going to do. And in this lesson, which is more of a walkthrough, I kind of coach you guys through how to do that. And so I'll kind of lay out a step. And the idea, hopefully, is you can try it on your own. And then I'll kind of do it and we'll just compare. So to find that point, if you think about it, what we're doing is that point is going to represent the intersection of the campground road, this line going from A to B, and this cabin site line that goes from the cabin site to wherever our hookup is. And again, point B is like down here, this triangle. Point A is up here at that triangle. And we actually don't know where this point where we're connecting is, but it looks like around 5.5. So to find that point, we've learned how to find the intersection point between two lines, but we need to have an equation for those two lines. So that's going to be our first step. That's what we're going to work towards. So I prompted us here. Our first step, well, if we want to know the equation of the line joining A and B, well, we better find the slope of that line, the slope of that road connecting A to B. So let's do that using our slope formula. And I've got lots of space on this slide, so I'll write out my slope formula. And I bet many of you guys are just really quick and can do this very fast, but I'm just going to show a lot of steps here. So we have 4.5 minus 8.5 over 10 minus 2, which gives us negative 4 over 8, or negative 1 over 2. So that's nice. That's not crazy difficult to work with, and it certainly looks like that. That makes sense. Down 1 over 2, down 1 over 2. It certainly looks reasonable. And I think one thing I didn't label on my graph is we're going to call the point where things hook up. We've used A, we've used B. We're going to call that point D. So again, we think that it meets about there. Call that point D. And I mentioned our key idea that the shortest route is always perpendicular to that line. So we've reviewed this in a previous lesson, but the slope of perpendicular lines are always negative reciprocals, right? And what's the negative reciprocal of negative 1 over 2? It's just 2. My wife's trying to sneak by. All right. Sorry, lots of distractions. Yeah, so the slope of the line from R to D, that side road we're building, would just be 2. And that seems to fit our rough diagram, right? It's always worth just consulting the diagram. Yeah, definitely a slope of 2 seems to make sense for that line. So we've got the slopes of our two lines. That's great. Now we just need the equations. So, and we've reviewed this skill too. So the equation of a line, y equals mx plus b. And we said that the slope for line AB was -1/2. And I've said, let's use the point 2, 8.5. But in reality, for that line, we know it goes through 2 points, 2, 8.5, and 10, 4.5. So we could have used any of those points. I'm just kind of giving you all the prompts for this one. Just really coaching you along the way. So y is 8.5. And let's leave that as -0.5 for now. That's okay. And that's just 2. X is 2 plus b. -0.5 times 2. 1/2 of 2 is 1. So that's -1. And we get that b equals 9.5. So the equation of AB is y equals -1/2x plus 9.5. Or, in this particular problem, I don't think it's so awful to use the decimal equivalent, -0.5x plus 9.5. Not a bad thing. Now, let's actually check to see if that makes sense. If we extend line AB back and think about what the y-intercept would be, does 9.5 make sense? Sure does. So we can be reasonably confident that we're on the right track. This is good. Let's continue and let's find the equation for the line for RD. So its slope was 2. And maybe just for completeness sake, just to parallel the previous example we did, I'll write out y equals mx plus b first. Yeah, but if you're in my class right now and you're wondering like why we practice that a lot as a review lesson, it's because we want to have that skill for right now. And we don't want that we don't want to be using all of our brain power just for this one part of the question, right? And we said for this line, the slope was 2. And if we think about it, for the side road, we don't know where point D is yet. All we know is that the cabin site is on that line. So we'll use 6 and 1.5 for our point. So 1.5 equals 2 times 6 plus b. 1.5 equals 12 plus b. So b equals negative 10.5. So the equation of RD, y equals 2x minus 10.5. Put a box around that too. Don't know why a box b there. I like to box my b for some reason. All right, so let's consult our diagram, make sure this makes sense. Now, it's not as easy to check this one, but I can see that side road from R to D, if I extend it back, negative 10.5 definitely doesn't seem out of place. So again, reasonably sure we're on the right track. All right, guys. Well, now we know the main road, the campground road, has the equation y equals minus 0.5x plus 9.5. The side road we want to build has the equation y equals 2x minus 10.5. Well, now we can find out where they meet, where that point D should be. And then we can get the construction crew to get planning and stuff like that, right? So our next step is to find the intersection of these two lines. So I'm going to call this equation 1, and I'm going to call this equation 2. Now you guys have those equations on your sheet, so I'm not going to rewrite them on my slide here, but I'm just setting those two equations equal, like we always do when we are finding the point of intersection, and it's in both lines or in y equals mx plus b form. Equals 2x minus 10.5. This equation, not too onerous for us to solve. Subtract 2x from each side. Negative 2.5x plus 9.5 equals negative 10.5. We'll subtract 9.5 from each side. Negative 2.5x. Now, negative 10.5 subtract 9.5 gives you negative 20 exactly. And this is working out pretty good. If you divide that by negative 2.5, we get x equals 8. Does that make sense? Let's check our diagram. Does that make sense? X equals 8 for point D? Sure does. And actually, I kind of just was a bit careful drawing my rough sketch, and my prediction was perfect. It actually is exactly at x equals 8. So that's great to know. So let's just find the y value. Looks like it should be about 5.5. So I'm going to sub that into equation 2. The y value, 2 times 8 minus 10.5. Yeah, 16 minus 10.5. Awesome. So we found the point of intersection is our point D, and it's 8, 5.5. So right away, that's very useful because we can pinpoint that to the construction crew and say that's where we're connecting the two roads. And then they can begin their surveying or what have you to build a road through that forest. They know exactly where the meetup should be. So that in itself is very useful. And sometimes all we're concerned about is where that meeting point should be. Some questions, finding that point where it connects the shortest route is enough, but we're going to go a little bit farther. We're going to find the length of this shortest route. And if you recall, we have a formula for the distance between 2 points, and it looked like this. So the distance, or the length of RD, and in my lessons here, I've been using D, and sometimes I might use L for length. I just kind of flip-flop sometimes. Yes, there's our length formula, guys. And I think maybe for this one, I'm just going to actually just get my points in here. R on this slide, 6, 1.5. I think this helps a lot of people. And our point of intersection, D, was 8, 5.5. And let's call this X1, Y1, and X2, Y2. So let's find that distance. So 8 minus 6 squared, and 5.5 minus 1.5 squared. This is actually working pretty good. So that's 2 squared, which is, I'll just show a lot of work. 2 squared plus 4 squared. I don't know why my square root was so big. Don't need all that stuff. But let's go up here. So that's 4 plus 16. That's the root of 20, which is exact. But let's get that decimal approximation. So the root of 20. And I'm going to keep, just for now, if you would, I'm going to keep a lot of accuracy. 4.4721, I'll say, units. Now, why am I keeping a lot of accuracy? Because remember, every unit on our grid was 500 meters. So the shortest route, sorry, that's Asher. He's fine. He just likes to scream. The shortest route is, so we take that 4.4721 and times it by 500 meters. And I think probably that was a little too much accuracy than we needed. Yeah, so the shortest route to the nearest meter, I got 2,236 meters. That's my dog wanting to come up from downstairs. Come on. But yeah, guys, we just found the shortest distance. And if we just review the steps we did. So 1, we found the equation of each of those lines. And that involved finding their slopes, doing y equals mx plus b and plugging in the slope and a point like we usually do. We used our substitution method to find a point of intersection. And then we used the length formula. And I would argue every little bit there was manageable. We know how to find equations and slope. We know how to find points of intersection. We spent a whole unit on that. And we know how to find length. Every step is manageable. It's just putting it all together can be the challenge, right? And again, just walking through those steps. We need the slope and equation of the given line. So that was from A to B. We did a negative reciprocal, and we found the equation of the shortest route. So now that we have those two lines, find the point of intersection, and then you can find the distance. And I've added a note here. You'll notice, hopefully you noticed, every time I did a calculation, I went back to my diagram and I double checked it, because that's going to help you catch mistakes, and that's going to help you give you confidence to keep moving forward. So I kept checking back, and every time I saw that things were lining up, it just made me feel more and more comfortable and just feel better about how the problem is going. Because this is a pretty involved question, but I just knew every step of the way I was doing fine because I kept checking my diagram. I have tutored kids who say, they're like, well, I'm not allowed to use the diagram, which I just find silly. Yeah, sure, we want to be able to do this algebraically, but having just even a rough sketch is so helpful just to keep checking answers. You guys in my class, we will do another one or two of these structured as a walkthrough from me, just to kind of get the hang of it and get another example in our notes. And then in our next lesson, whenever that may be, we're going to, it's really cool. We're kind of completely switching gears, doing something brand new. You guys know how to find the equation of a line, but I'm going to show you guys how we can determine the equation of a circle on the Cartesian plane. And then we'll be able to talk about triangles, circles, quadrilaterals, and a whole bunch of interesting properties about them that maybe you never heard about before. So that's going to be a lot of fun. Really looking forward to it. But until then, hope you guys are staying well. Have a great day, and we'll see you soon.